So, by the way, I'm sure this is included somewhere in Norbert Wiener's book on cybernetics. So I have things to tell you beforehand. There's a shocking video that I want people to see. So I do hope that you can see this. So first, I'd like to say it's a really great honor to give this colloquium. Norbert Wiener is a hero of mine, and because I am descended from a Harvard family and had queried my ancestors, it was pretty clear that I had no relation whatsoever with Norbert Wiener. And then to my great shock, my father said, "Oh, do you mean the Norbert Wiener from MIT?" He said this several years ago, and I'm not going to tell you the end of the story till afterwards because I want you to pay attention until the end. And it was really a shock to me. And it's a side of Norbert Wiener that very few people know about. But Norbert Wiener lectured to my father at Williams College in Massachusetts in 1948. And my father remembered this, although he had no idea who Norbert Wiener was. He was so impressed or depressed by the lecture. Okay, so I'm going to talk about three topics, all somewhat related to a very simple object. So probably the most simple object is in mathematics is plus and minus 1. So here's a function that looks like a Haar function. You take an interval, you divide it in half, and you put minus 1 on the left-hand side and plus 1 on the right-hand side. And that's the definition of HI. Okay? So now, then there's a beautiful theorem. I'm afraid to use this because maybe I can use this one. So if I take a probability measure, a Borel probability measure on the closed unit interval, then it has a unique product representation in terms of these super simple functions. Okay? And it looks like this. You take all possible intervals and you take some product and you take this in terms of the lengths of the intervals. Which intervals? Well, it's the usual dyadic tree. So think of this as being the unit interval. And the first interval we get is 1. And then you take a function which is minus 1 on the right, plus 1 on the left, and you choose a coefficient a sub I, and there's a restriction here on the coefficients that the coefficients have to be between plus 1 and minus 1. Okay? And the first time you do this, you pick, say, some coefficient a, and you get a function that's 1 minus a on the left and 1 plus a on the right. And you notice that its integral is 1. So if you start with 1 as your initial approximation to measure, which means it's a probability measure, you still integrate out after the second time to 1. Now let's pick two numbers c and d for these two. So if we then continue in the product, we get 1 minus a times 1 minus c, 1 minus a times 1 plus c. Right? Here c was chosen to be negative, so it went down. And over here we get these two. The integral of the red function over this interval is the same as that. And so it integrates out to that. And the same with this. So it integrates out to that. So the integral is 1. And now you continue down through the dyadic tree. You keep chopping and chopping and chopping. And you check out that you always have something that integrates to 1, and it converges to a Borel probability measure. And this is actually 1 to 1. If you hand me a Borel measure, then I will tell you the unique coefficients that give rise to it. So the only thing you have to do is be careful about the values of these functions at endpoints, because you could have a Dirac delta. So there's an easy convention for that. And you also need a convention if, say, AI is -1 or +1, because then one of these two things will be 0. And you'll blot out the mass of the measure on some interval. Okay, but this is a great fact, okay? And for many purposes, it's much better to make this representation than to, for example, expand in a standard Haar series or wavelet series. And the reason is there's a test in mathematics. A method is doubly good if you can both analyze and synthesize. If you take a positive measure, you can obviously expand it in any wavelet basis you like. That's great. But can you synthesize it? No, you cannot. You have to be very careful because things have to add up to be positive. And so it's very delicate. Whereas here, you've boxed yourself in. You're forced to stay in here. And it turns out these coefficients, AI, are just telling you about the relative measure on the left half and the right half of the interval. Now, is this a purely one-dimensional result? No, you can do it in 2 dimensions. So let's take the unit square. Okay? And now I'm going to do something a little strange. So here's the unit square again. I'm going to make a function. So this I would call maybe HQ, where Q is this square. And then I have -1 and +1, and I add that into the product with a coefficient. So now I've captured the mass on the left and the right-hand side of the unit square when I've done this. And the next thing I want to do is divide in half again, so I come down back to squares, not rectangles, back to squares. So what I do on each side here is now I take, say, this square, here it is, and I take the function that's -1 on the bottom, +1 on the top, and I form, so these are in the x direction, and this I would call HQ left, because this is the left-hand rectangle, and now I have a product of 1 plus AQ, HQ that sees things in the x direction, and then I have products of things that see things in the y direction. These pick out differences in the y direction. And then there's a term for the right-hand side also. They're still working on this. Okay, this is great. This is going to be an old-fashioned chalk talk. Okay? All right, I can put this down, that means. Okay, so that's great. And here's what we are supposed to see. You have to now imagine that you are seeing the following. So first I'm gonna put up a shocking video. This is a very interesting video. Probably all of you are aware of the financial collapse following Lehman Brothers. And if you open up your newspaper, your favorite economics-related journal, you see pictures of stock prices, but they never show the stock volume. Now, stock volume is nice. It's positive. Volume is never negative. By the way, that's also a very important concept in telecommunications. You tend not to have negative volume, right? And I'm going to show you, I guess it's going to be 14 different high-frequency trading streams over a 4-year period, approximately 4-year period of the economic collapse. And I'm sure none of you have ever seen this. Now, I don't actually have this data. I'm trying desperately to get my hands on this data to analyze it. Something very, very strange happened. And when it comes, I want you to look at August 5th, 2011. There's an undetected event. It was undetected up until about 6 or 7 days ago when this video was released. Something bad happened. And if you want to secretly Google this date, you can try and figure out what happened on that day, which had very strange effects. Okay, so next we're going to try and eventually look at telecommunications. So I'd like to think that Norbert Wiener would like applications of things like this to telecommunications. 3, Norbert Wiener was a master of measure theory. So I want to take a poll. How many of you have read his original paper on Brownian motion? Raise your hand. Raise your hand. Not that many. You should read it. It's really stunning, right? There were no books on measure theory at this time, right? It's in the 1920s, all right? And it just sort of comes out of the blue, and we'll do something Norbert Wiener-like with diffusion here. So then we're going to do something in geometric measure theory, which seems to be completely unrelated, but comes out of looking at the same formalisms and some strange signal processing in pure Fourier harmonic analysis. And then 4 is going to be a topic in conformal field theory, statistical physics, where you have these strange objects. What do we have? Do we have a signal? Signal to noise ratio is... What can you open?
I can only open the GIF.
Oh, we'll open the GIF. That's fun. All right, okay. And I'll start there. And I'll then describe while we're looking at the GIF. Blow it up all the way. It can be... Oh, it went away. So you can enlarge it. There should be a magnifier. Oh, there it is up there. Oh, it won't let us magnify. Okay, well, always working on it. It's scary enough so that maybe it doesn't need to be blown up, okay? What you're watching here is, I'll have to read off the dates for you. These are 14, I think, different exchanges in the United States. And this is not just stock trading data. This is high-frequency, algorithmic-driven data. So robots, as they're called in the trade, are drawing this. And so the robots are now going to work. It is April 20-something, 2009. And you see all these various channels. Now, there's one thing immediate you see about these. These signals are bursty. These are not smooth. It turns out if you have smooth things, you're probably better off using wavelet-like techniques to study them. But for very bursty signals, this is not the case. And they're much better studied by this. And how do you do that? You simply, oh, look, it's getting crazier. So it's now in 2010. Things have already gone bad, all right? So the way you do this is you normalize the volume to be 1. You just declare the total volume to be 1 for a day. And then you have these, right? And then you have all the coefficients. And the coefficients tell you how bursty the volume is, how spiky it is. In the synthesis direction, we can decide how spiky we want our probability distribution to be. It's getting worse, right? Oh, okay, now we're coming to the point. It is June 22nd, 2011. I'll count down to to August 5th. July, August 2nd. Boom. Does anyone know what happened on August 5th? It goes crazy. Moody's downgraded the United States. If you looked at the stock prices, you saw nothing. Nothing. There's just no event. No one has been able to figure out what's going on here in the past week, in any case, since this data was made available. Okay, it's sufficiently scary that I think we can now turn it off. You want to turn that off?
So when you say analyze the coefficients, are you thinking of them as like some little LP space? What do you mean by?
No. So what is a characteristic of bursty data is the following. By the way, this is a proof you actually do have to still prepare your lectures, right? It's not the case that you can still walk in. I forgot where 0 is. All right. So here's -1, here's +1. Let me draw a probability density, a PDF. So the integral of this function is 1. And the idea is you pick the AI chosen randomly from that particular PDF. The more spread out the PDF is, especially towards plus and -1, the more bursty the signal is, and vice versa. Okay, and they're all sorts. I'll show you some pictures, maybe tomorrow. Let me show you how you would now, for example, synthesize and analyze, and if we're lucky, we'll get to see a hurricane and what it did to telecommunication networks. So let me go over here. So let me describe one of the pictures you're going to see, I hope. Okay, so instead of taking time between 0 and 1, I'm going to periodize it. So think of a 24-hour clock, and we're going to put some probability measure on the unit circle. Okay, so now the unit circle, just like the unit interval, carries with it a natural grid. So here it is. I mean, the first thing you do is you have, here's 0, and you think of angle pi, and you cut like this. All right, and that divides into 2 arcs of the same length, pi, and then you cut again, and then you cut again, and you keep on cutting. Now this has a nice display picture, which is actually the Fourier picture. There's a phase plane picture here, but you should think of this on the upper half plane, right, where you've probably seen the picture. So, well, I'm going to draw a slightly smaller circle. Okay. And here we're supposed to recognize that we're going to pick one coefficient for the top and the bottom. Okay. And now, once I've done the top and the bottom, I have 2 intervals, so I want to cut them like that. Okay. So this sector corresponds to the entire interval from 0 to pi. This sector goes to there. So now I pick a coefficient B and a coefficient C. And now I keep doing this. So I cut, cut, cut. That was supposed to go over there. All right? And this line is going to continue down. And now I have C, D, E, and F. Oh, and do we now have, no, now we have nothing, I guess. Have we given up here? We've given up for the moment. Huh?
They are looking for better help.
They're looking for better help. Okay. Okay, so actually, from what I know of Norbert Wiener, he would have really liked this talk, right? Okay, so now when you do this, what does the coefficient D, for example, tell you? It tells you that if you go down here, then you measure, you have an interval on the circle, and you have a mass on the left and the mass on the right. And what the coefficient d does is it tells you the measure on the right over the measure on the left. So how does it do it? Well, here's a left and a right. And so the mu of the right over the mu of the left, well, the relative measure, this is the total measure here is 1 plus a over 2. The one on the bottom is 1 minus a over 2, and when we divide, those go away. All right. So a just tells us that ratio, and if we have a measure, of course we know these ratios, and so we get a unique value of a. All right, and so then I'll show you, I'm pretty sure we'll get this up at some point. I'll show you some telecommunication data. And one is from alarm failures in a hurricane. And the second one is much more fun for me because it's a proprietary data set, so I'm not allowed to tell you exactly what it is. but here's what it is. So you have lots of cell towers, 180 something, and you're looking at the traffic volume over these cell towers for a period of several weeks. And now the problem is, can you classify the days? Well, of course you can classify the days. They're different, right? And if you think of the volume of the traffic on Monday, you know this is going to be different than Wednesday, right? On Monday morning, people are still asleep, right? They're not on the telephone, right? And so it's not surprising you can do something, but you have to remember that communications networks work in places where you don't know the local environment, and the environment is both physical and sociological, right? And so things that may not be obvious can be detected very easily, and simply by looking at the coefficients and doing some elementary nonlinear statistics. So we have telephone towers, traffic. One can classify this. Okay. Now let me go over to a chalk talk, okay? And let's see. Now this is going to be an easier exercise. Raise your hand if you have taken a calculus course at some time in your life. Okay. Okay. So, good. Okay. I think everyone learned in calculus that if you have a graph y equals f of x, then the graph has a tangent if you have some sort of notion of differentiability, right? So let's just draw the classical thing. All right, so here we go. By the way, I try never to teach calculus at Yale, right? It's the hardest class to teach. It's much easier to teach Fourier analysis, right? Because I understand the questions. And in calculus, I can never understand the questions. Okay, so let's look at this. So here's a point, y equals f of x. And here's what a tangent is. Oh, well, we associate a line. And let me redraw this graph. Unfortunately. Okay, so here's x f of x. So how is it that you explain to the students what this is? Well, you say, well, if it were a hill, this would be, the slope that you go down. And they say, yeah, but it smashes into each other, so what do you mean? Well, it's the local one. And here's a good answer for a good student. The tangent line, or in higher dimensions, the tangent plane, mostly avoids the graph. So it does it locally, and then when you go more globally, well, you have to be careful. It could have a massive intersection with it, or it might not. But locally, it has pretty small intersections. So everyone learned that. And the surprising fact is that sets have tangents. And I mean sets of positive Lebesgue measure. So this is a much stranger notion. So that's a tangent. So sets have tangents. Okay, so let me write down a theorem. Now this is very strange. This theorem appears to be a statement in absolutely pure mathematics, but the entire proof is done by methods of signal processing. And the result has nothing to do with signal processing. There are filters, there are singular integrals, there are scales, everything. So let me state it in the case where I have a Lebesgue measurable set. How many of you learned Lebesgue measure in high school? Okay, that makes me happy. I recently had a 12-year-old student who's now at Princeton as a graduate student who did that. I didn't either. Okay, so we have a Lebesgue measurable set. So just
Where?
at Yale.
No. Where's
Oh.
Eli live?
Princeton. Let me localize it. Let me do it in the plane, okay? But this is a statement about, what, you expect me to remember my password? No. What happened? Oh, it's in. All right. It's not. So it's not supposed to be that one. It's the other one. Yes. Okay. And now it's at an angle. Look at that. That is quite... By the way, it turns out topic 3 is the angle. It's actually about distorted images. Okay? Maybe I should go to topic 3 then. All right, so... okay, yeah, all right. Don't touch, I understand. Imagine you are watching an analog television in the late 1950s, okay? All right, so I think I'll have to do this manually. Okay, so there's some joint work, 3 different things. Let's go look at the pictures. All right. Okay. Rock strata. That gives you a beautiful measure. Geologists know how to turn this into a measure. You go down like this. Look at the size of the rock of the different strata. Okay. This is supposed to be my funniest joke of the afternoon, but no one is laughing yet, so please allow me to explain. This is the Sara Lee Corporation. 4 is the time that the stock exchange closes. It says 4 p.m. here. Okay? It starts at 9:30. This is on, I can't remember which day. 1st of May, 2009, I believe. And you see the standard graph up here. It's not the standard graph, by the way. There's massive arbitrage going on here. So I like to show this to MBA students to tell them that stock movement is not geometric Brownian motion. There it is. Nonetheless, it looks vaguely like stock movement. What we're going to talk about today is this. So this is an example of a bursty signal. All volume of anything, forex trading, foreign exchange trading, stock trading, commodity trading, any trading is bursty by its nature. Most dynamical systems that produce measures, almost all of them, produce bursty measures. And now the strange thing that happens is we're going to take random data like this given by Norbert Wiener, and we're going to turn it into SLE processes. That's something in conformal field theory. That's why I chose that particular SOC. It's not that I like their ham or their underwear. It's a very strange company. But the amazing thing is this product formula is going to be a guide for us in conformal field theory and tell us how to build strange curves. Oops, sorry. Here's the product formula again. Here are the Haar functions. Here's the statement about relative volume that I wrote down over there. Okay. That is a bursty signal. Okay, so here what one has done is you've chosen these AI from a particular probability density function on +1, -1, and you can see this bursty behavior, and you see why the engineers call it bursty. Here's the picture that I was drawing with the unit circle. Okay, so I'm going to show you how that picture was made. So you divide up the interval into dyadic arcs, then you pull them in this canonical way, and then you just color them with the usual scheme where red is +1, blue is -1. Very red means your coefficient is around +1. Very blue means it's around -1. And so that's a color scheme, and it equals, so that color scheme gives you that. Okay, so that's synthesis. And so this is to show you that you can pick. This is a measure now done. This is very bursty. It's chosen with the uniform distribution, which puts a lot of weight out near -1 and +1, so it can become very bursty. And you can compute all sorts of entropies and stuff about this measure.
Well, are you starting with the AIs in some way, and then building up your signal, or
Yeah. So these are the AIs. The colors give you the AIs, and then I build that signal out of those coefficients by multiplying out this product.
no synthesis?
That is synthesis. Now I'm going to show you analysis. So this is weather data from a hurricane, and there are 3 massive failures. Here, lots of alarms go off, and then there's silence. Okay. And here's an example to show you that you get local information out of this. So the signal is over here. It looks very smooth to you. There's a little teeny area here that's been blown up there, and there it's rather bursty, and so you get coefficients for that area that are large, and then it calms down on smaller scales. That's an actual measurement from telecommunication data. Let me just skip to the second one. So here's the antennas. 182 antennas, 14 days of data. Just take all the data for all the days, take the coefficients, and do some sort of standard nonlinear statistics using diffusion geometry, and they classify themselves. It's no surprise to anyone that Saturday, Sunday, and Monday are all the same day, because Saturday you get prepared to watch football, Sunday you watch football, and Monday you recover from watching football. The interesting thing about this data set is it automatically detected that these people were still celebrating their football game on Tuesday. Okay. And that's why I'm not allowed to tell you where this came from. Okay, but that's what happened. Right? That was what was going on. Okay, so now we're in topic 2. I have about 3 minutes left, I think. So here's Rademacher's theorem. I have 13 minutes left. So here's Rademacher's theorem. This is a super classical theorem from about 1935. You have a function defined on Euclidean space. It maps to another Euclidean space. It's Lipschitz. F of x minus f of y is bounded by constant times x minus y. Example, f of x minus f of y is bounded by x minus y. That's a Lipschitz function. Rademacher has a beautiful theorem that such a function is almost everywhere differentiable. The way you prove this in calculus is you draw this function, absolute value of x. And it's differentiable everywhere except the origin. It's Lipschitz with constant 1. Rademacher's theorem is just a little bit harder than that, but it's not that hard. Okay. And now the strange question that's been open for, well, since Rademacher's theorem is this optimal? In other words, so if you're given a set of Lebesgue measure null on Rn, is there a Lipschitz mapping that's globally defined, but it's not differentiable at any of the points on E? This turns out to be an exercise on the line. Let me draw you the proof. So it's hard to see a set of measure 0 because it has measure 0. So I'm going to cover it by a small collection of intervals. And I'm going to write down a function by writing down its derivative. So I'll write down f prime, and I'll put plus 1 here. And the derivative there looks like plus 1. But now, since it has measure 0, on each of these intervals, I can go inside and take a very small collection of intervals, some of whose length is much, much smaller than this, and I can change the definition here from plus 1 to minus 1. And so the derivative looks like minus 1. And now I go back inside those, and you do this infinitely often. It gives you a nice function which is either 0, plus 1, or minus 1, and there's no derivative. It's easy to check, right? Because the function thinks it has derivative plus 1, and then it thinks it has derivative minus 1, and then etc. Okay? Now, the geometry of doing things like this gets much more complicated in higher dimensions, and it was only a couple years ago that this was done in R2. And the reason one could do it in R2 is one had, one, a very large geometric machine to, given objects like this, construct functions. But then you had to find these nice structures in R2, and you need something much more complicated. And then there's a trick in R2. There's strange combinatorics, again from the 1930s, due to Erdős and his co-author Sekeres, that allow you to rearrange sets into very special pieces. And it only works in R2 because the combinatorics that correspond to it in R3 and higher are unknown. Well, that's interesting. So that got... By the way, if you look up Lipschitz on Wikipedia, I just stole that picture. There it is. Okay? So the short story is that the theorem is proven by showing that there's something called a tangent field, which is kind of like a tangent cone, except now it doesn't make any sense. Right? Probably. But here's the definition. So remember that a tangent line has the property that it hits the graph not very much, just a little. And a tangent field is, again, a direction, and if you go in that direction, you don't hit much of the set. So let's draw a picture of that. All right, so here's a Lipschitz curve. It turns out that you measure these things with Lipschitz curves. So I get to pick a point in my set E. That's the center. And now I pick a Lipschitz curve. So here, the tangent cone is going to be a double tangent cone that goes this way and that way. And what I'm going to demand is that my set not hit this Lipschitz curve in very much of the set. So let's look at a picture of that. Whoop! It erased my picture. Oh my. Okay. It actually erased part of the file. So let me draw you a picture in R2. Here's a set of measure epsilon. Okay? In the unit square. It has side length square root of epsilon. Suppose I pick a point in the set in any direction, and I draw a Lipschitz curve approximately in that direction. So let's call that curve gamma. Then the length of the square intersect gamma is going to be bigger than or equal to epsilon to the 1/2 because it has to go through. Now the question is, if you're given a set E, can you write it in a controlled fashion so a fixed number of pieces so that each piece looks like this. It has a different tangent direction. So your set might be composed of things that look like this as well as little things that go like that. Okay? And they could be pointing in all directions, like Kakeya sets. And there's the theorem, theorem 2. Okay? There's some theorem you can do. So let me show you where the signal processing comes into this problem, even though maybe the problem isn't so clear. So remember I said in the very beginning that in 2D you can take 3 types of Haar functions and expand an arbitrary Borel measure in the unit square in this, and then it factors into things that see the x direction and things that see the y direction. So now we're going to take a special example of one. You take your set of measure epsilon, which is positive, and then that set is epsilon times a probability measure. All right? And so, because this is a positive measure, whose measure is epsilon. Okay? So after multiplying by epsilon, you get a probability measure. And you can decompose this. And now, if we just go back and look at this thing, oops, we've decomposed it into a product. One that sees the x direction, one that sees the y direction. So we have a product, and let's go look at it. Well, over here, so it's all breaking down. Okay. Over here we have 1. Here we have epsilon times 2 things. If this side is 1 and we have an epsilon here, one of these must be big. How big? Well, they can't be both less than epsilon to the minus 1/2. So one of these guys is bigger than epsilon to the minus 1/2. Let's make it the x one. And now we have this very strange product which is somehow derived from the set but doesn't capture all the information. But look, we're back in the situation over on the right-hand board. We have this product, we know nothing about it except that its coefficients are legal. So if I integrate along any line, I get 1. Okay? And if you stare at the previous thing, this shows that if you take the set E and divide it up into 2 pieces, according to which whether this is big or that is big, let's say E sub x is big, we'll call that E1, then you get the estimate on the bottom. Right? Since the product is big and you integrate out to 1, the length has to be small. Right? So the length of this set where the product is big has to be small. How small? Epsilon to the 1/2. Okay? Okay, so you've just given an estimate for this picture. Oops, where'd it go? Things are disappearing here. Okay. So the integral along this curve will be small if the curve is a straight line. Okay? Now it turns out if I know this for all reasonable Lipschitz curves, you get a miraculous rearrangement of your set. You can build nice strips that cover it in a beautiful way that allow you to copy the one-dimensional Rademacher proof. And the problem is you've only done this on one line. You need this on all possible Lipschitz curves that go through the set. So let me draw a Lipschitz curve. It's an infinite dimensional space. It's not a finite dimensional space. It turns out that it's easy to perturb this theorem very slightly and break up your set into a small number of pieces so that you can integrate along straight lines in a very small cone. But that's a finite dimensional space, and you need this. And then you have to start working very hard. So how do you do this? Copy Wiener. Filter. Okay? Change your measure by changing your basis. Okay, so you pick very strange filters associated to this that allow you to integrate over lines. And then you use geometric measure theory about Lipschitz curves. And you have to check that you haven't changed very much. And it gets worse. All of these objects are non-smooth. And all the estimates you need on smoothness. So what would any reasonable engineer do? He would take this formula and spin cycle it. You would translate dyadic grid over all possible translations, take averages in some manner. And then when you average functions that are plus and minus 1, they become smoother. They're no longer discontinuous. So they become Lipschitz. Okay. Let me just end with one final set of pictures because I think we've run out of time. This is an SLE curve, okay? This is two Fields medals, okay? At the two most recent international congresses. How do you get it? It comes from a very simple ODE, which you can solve. You run Wiener's favorite thing. There's Wiener, right there. Brownian motion. You take the space of all Brownian trajectories. You pick a parameter kappa, and you solve this in the upper half plane. You get a conformal map that starts at the identity and starts shaking and maps the upper half plane to itself. And it maps the upper half plane to itself minus a strange curve that looks like this and depends on kappa. Okay, everyone understand that? Because that's two Fields medals right there. Okay. This is a dynamic procedure. Right? Physicists observe this as a static object. It shows up in places like magnets, easing boundaries. There's a whole collection of various values of kappa. Loop arrays to random walk, Brownian frontier, harmonic explorer, percolation clusters, uniform spanning tree, strange limits of traveling salesman problems. And what I want to end in is to show you that there's a way to use this formalism to recover these previously dynamically produced objects in a completely different way that relates to the beautiful pictures you've seen. So imagine that you actually had a good lecturer like last night, right, showing you beautiful pictures. So I'm going to show you some beautiful pictures, and they come from something called a dictionary. So a dictionary is something that relates two different fields where you can translate theorems, concepts, and proofs. Okay? Can you do it all the time? No, but mostly. It's like a Rosetta Stone where you can go across. And so if any of you have seen beautiful Julia sets or something, one of the worlds is going to be Julia sets. The other one is world related to hyperbolic manifolds called Kleinian groups. It also has the same sort of beautiful pictures as here. These were known to be related. And this other procedure that I'm showing allows you to fit this in with that world. And here we go. So let's just look at some pictures. Okay, so there's a parameter space. There's Wiener, right? You're forced to work with Wiener space. Okay, that's a Julia set. This turns out to be a Kleinian group seen from inside a three-dimensional hyperbolic manifold, a place you probably have not lived. Okay, so let me show you a picture of one you've probably seen. There, that's a picture on the plane. It's a gasket, Apollonian gasket type thing. You have circles, and there's some group of Möbius transformations that take circles to circles, and these disks to disks, and then there's something left over which is called a limit set, and it's kind of like a Julia set. Here's another very strange one. This is actually a picture of two Riemann surfaces, believe it or not. So you take two Riemann surfaces of the same conformal type, that was just like a double donut, and then you twist it. You go, that's one Riemann surface, and then you go, you make, say, the donut very long and thin or something, and topologically they're the same, but conformally they're not. And then it turns out there's an amazing theorem due to Lippmann bears, which is a theorem in analysis, that says that there's a curve that corresponds to it, some strange fractal curve in a group, and somehow the outside is one Riemann surface and the inside is another Riemann surface. And there's a mechanism to build these curves by solving an order 1 differential equation. This is not a trivial differential equation to solve. You're looking for homeomorphisms where the d and the d bar derivatives of complex analysis are somehow related to each other. And this is classically done under cases where you can solve it. And the short story is this. All right, so there's Norbert again. So you want to prove that there are pictures like this that arise somehow from probabilistic data and give these SLE curves. And I want to show you, as my last slide, where these guys come from. Most expensive image, so about $1 billion have now been spent on this image. Does anyone recognize this? Yes. Yeah, this is called WMAP, right? The astrophysicists would go nuts to see it distorted, right? They spent hundreds of millions of dollars on the image processing. This is the microwave background. What is the microwave background? Okay, so it comes, surprisingly, according to the most believed, whatever that means, physical models. This is a picture. You are seeing a picture of the early universe at time 10 to the minus 35 seconds. It's frozen. Something happens. The universe undergoes a fantastic expansion. It's not the particles in it that moves, it's the space. It doesn't violate anything. The space explodes. Points that used to be in the same light cone are now out of the light cones. It's called inflation theory. And it predicted this picture. Why? It predicted a particular signature of this picture, which is called by mathematicians, it's called the Gaussian free field. By physicists, it's called the massless free field. It randomly distributes energy, and every scale has the same amount of energy, and every location has the same amount of energy, almost. So you randomize it, and it has a Wienerian definition. So let me just show it. Here's how you do it on the circle. This is a Fourier series. You take sine j theta, cosine j theta. I'm going to throw in j to the minus 1/2 here. I'm going to subtract something strange. And these are just Gaussians, whose variance is t. So this, if these are randomly chosen, these are IID Gaussians, then you get a series which does not converge anywhere. Okay? Now the strange thing is, if you exponentiate it, it must get worse. It gets better, right? You somehow subtract minus infinity because the sum over j of 1 over 2j is plus infinity. Okay, so you add things up. And now, when you do that, there's a beautiful theorem of Kahan that tells you get a nice measure. Now you need to produce curves out of it. Okay? And so here's what you do. It turns out you are forced to write that measure on the unit circle like this and check how close these coefficients get to -1 and +1. If they're close, that's bad. So they're not allowed to get too close. And you actually use techniques of Wienerian Brownian motion and stochastic SDEs to estimate these coefficients when you do them. And there's a way of doing this with martingale methods. And finally, out of this measure, there's miraculously built a unique curve. And it turns out if you do this twice, you recover SLE. So I apologize for the loss of transmission here. Huh? You don't know that, actually. But I thank you very much for your attention. I'm happy to answer any questions.
Before I ask you any questions, let me just tell you something. When I was a student in Poland years ago, I've learned from one of my professors that there is one type of situation which allows you to very easily discriminate between mathematicians from the Eastern Bloc versus the Western Bloc. That's exactly when something breaks. So we walk away and things don't want to cooperate. That means there has to be a deeper reason. On the other hand, mathematicians from the West, when something breaks, they do not give up. And with this, I want to thank Travis, whom I'm not sure if he's here, that he never gave up in making something that did not want to work. He made it work. So with this, I will turn to questions to Professor Jones. It certainly would fool my professor in Poland, because his quick switch from slide to chalk makes him really a truly Polish mathematician.
In America, it's called faking it. Okay. Yes. Okay, so I thought there was absolutely zero relationship between me and Norbert Wiener, and then in the 90s, for the Wiener Centennial, I gave one of the addresses there, and my father called me on the phone and said, "So what are you doing?" And I said, "Oh, I'm going to MIT because I have to give a lecture." And he said, "Why?" And I said, it's called the Wiener Centennial. There was some guy named Wiener," and he said, "Norbert Wiener?" And I was totally shocked because my father is a medical doctor. A Gaussian random variable is pretty heavy material for him. And I said, "Yes." And he says, "From MIT, Professor Norbert Wiener." And I said, "Yes." And I said, "How do you know him?" And he said, "Oh, in 1948, I was an undergraduate at Williams College taking a class in political science. And on Tuesday, our professor told us that on Thursday, a great genius will come and lecture to you about political science." So we sat in the room, and a limousine pulled up outside. A fat man got out. He actually said that. It's not my words. He said a fat man got out, came in the building, and spoke for an hour, and then walked straight back into the limousine without taking any questions. And I said, "And what else do you remember about this?" He said, "No one understood a word," including the professor. And my father actually was so shocked by this manifestation that appeared in front of him that he remembered the name Norbert Wiener. It's pretty good, 1948, right? So I also I lobbied very hard to get the office into which Norbert Wiener was carried when he suffered his heart attack in Stockholm. And I came in second. So I was not allowed to have that office. I had the office underneath the office. And my sofa was in exactly the same position that the sofa was for Norbert Wiener. And I actually don't know if he made it to the hospital alive. And I would go up and look at the sofa that Norbert Wiener lay in. Unfortunately, it had been replaced by a modern sofa, but people who had been there in the 60s remembered this and assured me it was in the same position. And let me answer your second question, which is, so what was Norbert Wiener doing there? He was giving a lecture series at the Royal Institute of Technology. And Leonard Carlson told me the following fantastic story. He told me many stories about Wiener and visiting. And Carlson had been at MIT with Wiener, so that's how they knew each other. And he said that, so Wiener had this lecture series he was giving, and that he insisted to Leonard that he wanted to meet the undergraduate students who were math majors, and so he wanted to be taken to the math building after lunch. And here's what happened. He was taken to the math building, and he would stand, imagine this is the door, he would stand next to the door, and as the students came in, he would stick out his hand and say, "Hello, my name is Norbert Wiener. Which of my theorems is your favorite?" Now, I mean, it sounds like a joke, but Leonard Carlson just does not, I mean, I've pressed him many times very hard, and he said, "No, Peter, that's simply what happened."
Other questions? I guess it's difficult to top that story.
Okay, so what exactly is the finish of that? You started to write a theorem there. What's the...
So the theorem is that you can break your set up into a small number of pieces in such a way that if you take one of these sets, Ej, that it hits any Lipschitz curve going in its direction in very small length. This would be optimal, and we can do it with a small error in the exponent instead of 1/2. In higher dimensions, it's exactly the same picture, and then you have epsilon to the power 1 over d, and then we have to give up a small power of delta. And this allows for some strange covering of the set. You can split it up into d different pieces, one for each dimension. And then the set can be covered by very small strips. So I'll draw them. So the set for the x direction would look like this. You'd have extremely small strips covered by Lipschitz curves. These are Lipschitz curves. And they would cover the set, and you would mimic this proof. And at the next step, you have to go inside this and build even smaller, little teeny windy things that cover the complete set. And by the way, this is a completely different theorem than most harmonic analysis theorems, because you're not allowed an exceptional set. You have to cover every single point. It's about sets of measure 0 where it really gets hardest. So you're not allowed an exceptional sets. And methods of harmonic analysis, by their nature, produce small errors. And so one has to repeat this over and over and check very, very carefully that at the end there's nothing left whatsoever. Okay. So So here's what you do. There's a very simple picture in the background. So the picture is the following. Take a Jordan curve in the plane. This is a theorem about complex analysis. This is a Jordan curve. Okay? And I'll call it little gamma. And now let's first go back to our first course in complex variables, which tells us that if I have a Jordan curve, there are two associated Riemann mappings. There's a Riemann mapping H plus from the unit disk to the inside, and there's a conformal mapping from the outside of the unit disk to the outside. Now, it's a very old theorem from around 1912 or 14 of Carteadori that in the situation, both of these maps extend to be homeomorphisms of the boundary. So they map the circle to this curve, 1 to 1. Okay? Not smooth, nothing like that. The curve can be as nasty as you want, and the modulus of continuity is bad. Now, so let's just take S1 and do the following. We take H plus of e to the I theta. That's over here. Right? And now we map back by H minus. And that's e to the I phi of theta. And it's a composition of two 1-to-1 mappings, so it's 1 to 1. So this phi must be a homeo of S1. Okay. Now you could try to reverse this. So, and we say that gamma is what's called the welding curve for the homeomorphism phi. It's somehow you weld the two sides of the domain to each other and you get a homeomorphism. Now there's a converse problem. Suppose someone gives you a homeo. Is it a welding curve? Right? Is there an associated Jordan curve? Okay. So I'll show you a very strange example where this happens. This curve is built by somehow this method. You build a very strange homeomorphism of the unit circle related to you have two different Riemann surfaces of the same topological type. And then there's an algebraic formalism for constructing this. It involves solving a PDE. So there's a PDE that you solve. D bar F is mu dF. And mu comes in some very complicated fashion from this. And this would give you some sort of, well, this gives you the two Riemann mappings. Okay? So what you need to do is solve these. This is an elliptic type equation. And you know what? This formalism, as far as I know, was invented by, let's see, so we have Pfefferman, Koenig, and Jill Pfeiffer. So Robert Pfefferman, Carlos Koenig, and Jill Pfeiffer. It's the statement of the theorem is a proof in itself, but they studied things that could be potentially degenerate elliptic equations, and the measure in question corresponded to the Poisson kernel for the Laplace equation. Okay, so the kernel for the Laplace equation is a beautiful smooth measure, and you want to know how measures for various elliptic problems are. They're not smooth. So the interesting ones are not smooth. The question is, are they singular? Are they purely singular? Or are they just L1 functions, or maybe locally L2? So they prove some estimates in the elliptic case. This is a different elliptic case, actually. But the short story here is that what you do is you start with let's go back to the picture. It's kind of amazing. And I am not kidding when I say that this picture actually gave me the inspiration to do this work, because I understood the physics of this, and then I realized, oh, those are the unique physics that could possibly give rise to a theorem of this type. It turns out there's nothing else. So then you do this crazy thing. You take a massively divergent, well, it's a logarithmically divergent series. Right? So we take some, I'll write omega in honor of Wiener, because you're supposed to think of omega as being the point in the probability Wiener space. And then I take cosine j theta over square root of j. I do the same thing with the sine with another independent Gaussian. And then I subtract t over 2j, and the variance of this Gaussian is t. So if I sum on j, this diverges logarithmically. It doesn't converge anywhere. If you ignore this, right? It still diverges logarithmically. Now you exponentiate it, and this looks like an object in the Feynman-Katz formalism. Formally, its average value is 1. Right? So for each realization, you have a hope that this actually represents a measure. So you call this mu omega. And the theorem of Kahan is that if you restrict to the variance to be strictly less than 2, which corresponds to the Serre-Lee picture with time 4. Okay? It turns out the 2 corresponds to SLE4, and that's why I chose that picture. So then you form this measure, and now you normalize it. So you take mu, you divide it by its total mass, and you multiply by 2 pi. That's a measure of mass 2 pi. So it could be the derivative of a homeomorphism of the circle. And theorem, almost surely it is. In the sense of distributions, it's the derivative. And so you get the homeomorphism, and now there's this formalism that you go through to find the welding curve. And now notice this thing is oscillating. Right? Look at the oscillations here. Right? There are oscillations on every scale. And so you expect that the curve that you get will oscillate on every scale, and it does. And if we go back and look, let's now just go end by looking at oh, sorry. Here it comes. I've lost it. There it is. It looks like that. Yes. Yes, but the difference is it's not a dynamic picture, it's static. There's another difference. And this was the sticking point for a very long time in the field. You see, the SLE traces that are formed by solving a differential equation are infinite, and they cannot be turned into loops. They just can't. It turns out you can't renormalize them to be a Jordan curve without knowing how to normalize them to be Jordan curves, or renormalize them. And these are Jordan curves. So these are a local renormalized version of those guys. Okay. Well, so yeah, it got people to carefully calculate the following statistics, which is interesting because they're most easily done by a machine I don't understand at all, which is called quantum gravity. Because there are about 3 people who understand how to use this. It's a formal machine using formal methods and strange diagrams. It's the statistics of what one side of the curve looks like when it looks across at the other side. You know, if it goes in here, how much does it go in, and how does it look on the other side? So what we know is the 2 sides have to be statistically the same, but they're various exponents. There are an infinite number of exponents. And so the first step in checking these things, you had to check all these exponents to see that this methodology could give you the correct picture. And I think the biggest contribution is it produces what the physicists recognize, which is a static picture instead of a dynamic picture. It comes all at once. And it comes from the Gaussian free field, which is the best conformally invariant random field.
Any other questions? If not, let us thank our speaker again.